in this program. I'm a member of the PAN-microplast team. This is a network that promotes, facilitates, and encourages literal collaboration and research efforts, as well as knowledge exchange in micro and nano plastic pollution in Africa. I'd like to introduce our speaker for today in person of Dr. Andrews Mays. Andrews is a senior lecturer in the School of Chemistry at the University of East Anglia, United Kingdom. He is an expert in nano and polymeric materials. We only have an hour for this program. Andrews will make his presentation titled Practical Microplastic Detection with Nile Red from Schools Outreach to Do-It-Yourself Imaging Ring, after which we have our question and answer section. Please be informed that this webinar will be recorded for academic purpose only. Now, let's join Andrews as he gives his talk. Andrew, you are welcome, please.
Okay, so thank you very much and good day, everybody, whatever time zone you're in. And I'd like to thank you for inviting me to participate in this, this microplastic venture. And hopefully something I have to say today will be of use or of interest to you. And if you want to know more about things, please do feel free to contact me. And my email address is here at the bottom, andrew.mays@uea.ac.uk. So just in case you don't know where Norwich is, we're on the kind of eastern part of the UK. Here it's about 2 hours northeast of London by train, and we occupy a very nice leafy parkland campus kind of on the west edge of the city. And the chemistry department I've ringed in red here. Out the back we have a nice view of the boiler house chimneys, but my office has a nice view out here over to the lake. And UEA is relatively modern university. It was founded in 1963, particularly well known for environmental science, climate change research and so forth. Also creative writing and international development. But the chemistry department actually has been at UEA pretty much since the beginning. It's founded in 1964, and it's a UK top 20 chemistry department. So we're not one of the biggest, but we are a significant department in the UK. And I'd just like to start by saying that plastic litter and microplastics really is a truly global problem. And it's a problem that we face in the UK, maybe not quite as extremely as in some parts of the world, but it's very much something that we are very exercised about at the moment. And there's a lot of research going on in the UK academic community in relation to our own microplastic problem, as well as the global microplastic problem. So here's some pictures, some of my microplastic pictures from local beaches and so forth, and some samples typical of what many of you might also have seen. This is some that were picked out of a wastewater treatment plant sample, and typical, every colour of the rainbow is present in this, this sample. So how did I get involved in microplastics? Well, it's a bit bizarre in a way, because ironically and perhaps slightly embarrassingly, I've spent almost 30 years in academia as a polymer chemist. So I've been perfecting methods to generate microplastics deliberately in all kinds of shapes, sizes and forms for a very long time. And my interest was using these microplastic particles and films and so forth in various aspects of analytical science, particularly development of sensors, extraction and separation materials, and so forth. And it's really going back 8 years or so, people were starting to talk about microplastics. And I realized that all this experience I had in making microplastics and characterizing microplastics for completely non-environmental purposes was actually really relevant to this whole area. And so I set out to try and develop some new methodology to make microplastic analysis quicker and easier. And as part of that, I published a paper, which is by now quite widely cited, about using Nile Red for detection of microplastics. And since then, I've been working throughout the last 8 years or so on the microplastic problem, but largely I've been focused on trying to improve our own infrastructure to make it possible for us to measure and work with microplastics. And then particularly highlighting plastics in consumer products like bottled water, tea bags, wet wipes, and many other things. And I'm being particularly keen on trying to get the message out to the general public that there are plastics in all kinds of products and they need to be aware of it and think about what they do with them and how they dispose of them. I've also continued to work on making aspects of the Nile Red method better, and particularly to introduce industrial users in the water industry, for instance, to the possibilities of using this technique. And most recently, I've been involved in setting up a microplastic analysis network in Malaysia. And I'm going to say a bit about that at the end, because I think some of the things that we've done and some of the lessons from that may be very relevant to what you're trying to do through and across Africa at the moment. So there might be some parallels and links here that we can use to help with the development of the Pan-African network. Okay, so just as a starting point, there's some photos of the microplastic lab at UEA. So I've now got some nice laminar flow cabinets, but it took us a long time to get these. And it's really important to understand that you can do really good, careful microplastic work without access to these kinds of equipment. You have to be more careful, you have to be more rigorous, but you can do it. And we do a lot of work making our own equipment. So these are sediment separators based on the Exeter design. And these are examples of many microplastic related equipment that we've built ourselves. We have an infrared microscope, but it's not a really fancy one. We don't have an array detector for this. It's a single point detector, but we can do some good microplastic analysis with this. But I'm going to say more today really about other types of rigs you can use to detect microplastics and some of the really simple things you can do to help yourselves with analysis. So I'm not going to say very much about this because I'm sure you're all familiar with the many different methods that are used to detect microplastics, starting from the very simple physical visual sorting methods through spectroscopic methods, which are, of course, the gold standard, if you like, for microplastic analysis and identification currently. The problem with these techniques, of course, is that you need the instruments and that some of these instruments are very expensive and very inaccessible. So, as I said, we don't have a focal plane array instrument at UEA. We don't have a Raman microscope yet, but we'll be getting one relatively soon, happily. But, you know, this is technology that is not accessible to all people. So if you want to use it, you need to think smart and probably collaborate. Many of you will have been at the session last month where there was an excellent talk about the use of pyrolysis GC mass spec for microplastic detection. That's an emerging technique that I think is going to be increasingly important. Unfortunately, like many others, we don't have that set up at UEA currently because I don't have a suitable pyrolyzer system. But hopefully we'll be able to do something about that in the coming months. But the technique that I really want to focus on today is the various dye staining methods that are being used and developed for microplastic analysis. And these really offer simple, rapid, cost-effective methods that you can use to help you with your microplastic research. And the first publications in this, including my one that I highlighted earlier, they came out in 2016, 2017. But since then, there's been a very large number, of course, of publications using this technique or specifically publishing developments, evolutions, improvements of the basic staining methods that were reported in the early papers. But it's worth noting there are lots of myths, misunderstandings, and criticisms of these methods as well. And some of them are justified, and some of them I think aren't so justified. And that particularly revolves around issues with false positives, but also false negatives, which are much less discussed often, but they're undoubtedly also a part of the story. So what I want to do is to just highlight some of the advantages and opportunities of using these dye staining methods. And then I'm very happy to talk about any of the issues, myths, and so forth that anybody might want to discuss at the end. So what is Nile Red? Nile Red is a very typical dye molecule. It's a fused aromatic planar ring system, and it's got some electronic properties that make it highly fluorescent. And Nile Red's been known for very many years. It's been used widely in biology for staining particularly hydrophobic structures like neutral lipid droplets in algae, lipid membranes in various cell biology studies and so forth. And Nile Red has this general property that it dissolves in hydrophobic solvents or adsorbs onto hydrophobic surfaces. And when in those environments, it displays very strong, bright fluorescence. But a really interesting property of Nile Red is that it shows really strong solvatochromic behavior. And what this means is that the molecule itself and its electronic configuration is really, really sensitive to the environment in which it's sitting. And you can see this in some of the photos here. This is just Nile Red dissolved in various organic solvents. So you can see in hexane here, it's a very sort of greeny yellow color. But in some other solvents, much more polar solvents, like dimethyl formamide, for instance, it actually fluoresces a really bright red color. And this is both interesting and also possibly helpful and also possibly obstructive, depending what you're trying to do with your Nile Red detection. And I just wanted to show you the spectra, because it's really important to understand the spectra when you're thinking about designing a detection setup for Nile Red fluorescence. So I've superimposed a visible spectrum here, which is reasonably accurately scaled so that these colors represent the wavelengths on the x-axis here. And what this shows you is that when Nile Red is dissolved in a very hydrophobic solvent like toluene here, or down here we've got hexane and other hydrocarbons. These are much lower because the samples are diluted because they went off scale up here. So you can see when it's in very hydrophobic environments, it's really quite green, greeny yellow, the fluorescence. But in more polar environments, the fluorescence shifts very markedly to much more orange and red wavelengths. And this is really important when you're thinking about detecting your fluorescence. And I'll come back to that a little bit later. Okay, so Nile Red dye as a dilute solution, you can put it into a suspension of microplastic particles, or you can drop it directly onto plastic objects, and it will absorb and it will stain them quite brightly. And you can see here there's a whole variety of typical small bits of plastic. These all came from natural samples I picked up at the waterline on a beach. And stained with Nile Red, you can see that they all, pretty much all, fluoresce brightly. But it also shows you that the staining can be very, very variable. So I've highlighted a couple of pieces here, which are very dark coloured, and that's probably highly significant. Very dark coloured plastics, you can see they're not fluorescing very strongly here. There's a black one here, and you can see the surface of it isn't fluorescing at all, but you can see really bright fluorescence around the edges of it. Another piece here, this is a piece of spongy material. It's fluorescing incredibly brightly, so much so you can kind of see the glow of it all around. So the fluorescence is spreading out way away from the object itself. And this is because spongy materials, they're porous, they have a lot of surface area for dye absorption, so they absorb a lot of dye, and consequently they fluoresce very, very brightly. But in general, what you can probably note from this picture is that all the fluorescence is kind of yellowy to orange to quite red colours for some of these objects. And there's almost nothing here that's really fluorescing green. And that's very, very typical of what you see when you're looking at natural microplastics. Because actually, microplastics and small bits of plastic that have been out in the environment are typically less hydrophobic than you think they are. And the reason for that, well, two main reasons. One, they tend to get oxidized. And the second reason is they very often have biofilms on them. So algae, bacteria, and so forth, populating the surface of them, which means that the dye is in a slightly different environment from what you might think it would be in if it was on a pure, clean, pristine plastic surface. I should say, if you take virgin plastic, or you cut a piece of plastic to show a completely new, clean face of that material, if you absorb Nile Red onto that, you might see much greener colours in the fluorescence if you're looking at hydrophobic plastics like polythene, for instance. Okay, so does Nile Red detect all different kinds of plastics? And the answer is no, it probably doesn't, but it does absorb and fluoresce on the surface of a very wide range of different types of plastic. And some of them are shown along here. And it's undoubtedly true that the brightness of the fluorescence varies greatly from from sample to sample and plastic to plastic. But the absolute values here you should really take with a pinch of salt, because it depends very much on the nature of the bit of plastic you're looking at, on the surfaces it has, on the optical properties and smoothness of those surfaces, and so forth. So really, the take-home message from this is that Nile Red is capable of detecting most kinds of plastics, but there are a few things that you won't easily see. And the particular one that I would highlight here are black plastics. And this is, in a way, it's quite unfortunate because quite a bit of black plastic is used. Carbon black as a filler is very common in plastics, and black plastics are often desired because they reduce ultraviolet damage. So if you're going to use plastics outdoors, black is often quite a good color for them. And this means that quite a lot of plastic in the environment is black. And Nile Red is not always very good at picking up those black plastics. And the reason for this is probably not that the dye doesn't absorb to the plastic. I'm sure the dye does absorb to the plastic. There's no reason why it shouldn't. But the problem, I think, is an optical one. So remember, when you excite fluorescence, you have to get photons into the dye molecules. But when the fluorescent light is emitted, it can come out in any direction. And the light that goes in towards a black plastic will just be absorbed. So those photons are not scattered or reflected, and they don't come out in a direction where you can observe them. So the level of fluorescent light coming back from the surface of a black polymer is going to be very, very much less than it would be from a typical white or perhaps transparent polymer. And that's why they appear much duller, or possibly not even visible at all, when you use Nile Red detection methods. And you can see that from this series of different coloured PVC fragments stained here. So a white one shows up really brightly, really nicely. Blue and red ones, not too bad. But the black one you can see here is pretty dull, and you're only really getting a little bit of fluorescence from edges, thin edges perhaps, where you get a little bit more light penetration and a little bit more scattering. So that's an optical problem that you need to be aware of. And it's also a problem because it can lead to false negatives, missing particles that are present because they might be black. So that's always something you need to think about. But it should also be said that black polymers are actually quite difficult to get other types of data from as well. So infrared spectroscopy doesn't necessarily work terribly well on black polymers. Raman spectroscopy can be difficult with black polymers. So it's quite a general problem in microplastic analysis. Okay, so if you want to use Nile Red to detect microplastics, what do you actually need? And the answer is, at a kind of basic level, you need very little. You need some kind of light source that's going to excite the fluorescence. And usually a blue light source is the best wavelength to choose for that. Something between 450 and 480 nanometers would be ideal. You can actually buy lots of very good, cheap blue LED torches these days. So 10 to 20 pounds sterling buys you a really well-made metal-bodied torch. These are mass-produced in China. They have very good, often Cree LEDs in them. They're very bright. The problem with these cheap torches is that the optics that they have at the front of them to focus and control the light, they're not very sophisticated. So the beam quality, the intensity variation across the beam tends to be quite big with these types of torches. And that's why for most of the work I do in my lab, I much prefer these much more sophisticated, but also much more expensive torches, which are manufactured for forensic science purposes. So this is a crime light made by Foster and Freeman, and they are excellent because they have lots of clever stuff in the front here that ensures that you get a very uniform, even light across the beam area. And this makes them much more easy to use for high quality imaging work. So if you're just trying to follow something using your eyes, or you're just doing demonstrations and so forth, these cheap torches are absolutely fine. But if you want to do really high quality scientific imaging, you really need to think about the beam quality. And in that case, more sophisticated light sources definitely are much better. And the same applies for the filter you need, because in order to see the fluorescent light from your microplastics, you need to be able to block out the blue incident excitation light. And in order to do that, you need some kind of orange filter. And you can use lots of different types of materials for this. So at the simplest level, you can just buy a sheet of orange acetate film, costs next to nothing, and it works fine for many purposes. Equally, orange safety spectacles, if you're just observing things, orange safety specs work very well. They're designed to cut out blue light. For instance, the blue light that's used to cure dental enamels, or just general UV blocking safety specs for lab use or industrial use. They're quite inexpensive and they work pretty well. But again, if you want to do high quality scientific imaging, you really want a high quality glass orange filter. And it's important to emphasize that not all filters are equal. So I have a whole collection of cheap orange filters in my lab, all of which are pretty much useless for Nile Red detection because they leak blue light through them, which spoils the contrast and obscures the microplastics when you're trying to image. So if you're setting up a system, buy good quality glass filters. And I should comment that these kind of orange filters used to be used very widely for black and white photography to kind of highlight and emphasize the clouds in skies and so forth to increase the contrast. So there are loads of these lying around in drawers, and you may well find them wherever you work. If not, you can buy them on eBay. I've bought lots of them on eBay for scientific use, and providing they're not too badly scratched, they work absolutely fine. Okay, so what can you do with this kind of inexpensive equipment? Well, certainly you can use it for demos. So if you're doing schools outreach work or public community outreach work, and you're trying to explain to people what microplastics are and to show them that typical samples of soil or whatever contain microplastics, all you need is some orange goggles or orange acetate film and a blue torch. This is a not terribly good photo of a typical demonstration. This is one I have in my show and tell box, which is just some beach sand, some pebbles and so forth, and some typical bits of microplastics. In this case, they're actually ion exchange resin beads of various different types and sizes. And you can see here that they've formed a nice kind of layer in the settled sand that you can highlight and show using just by shining a blue light on it and observing it through an orange acetate film. So that's really useful, very simple detection. At the next level, and something that I used widely in my lab in the early days of working with Nile Red, it's just a binocular microscope, standard observation microscope that most people probably have in their lab. And all you need to do is cut a bit of your acetate sheet and stick it on the bottom where the optical windows are at the bottom here. So if you stick that on, you can just use sticky tape along the sides to hold it in place. And then if you illuminate your Nile Red stained sample with a blue torch, you can just hold it in a retort stand, or you can do something a bit fancier with clamps and things if you want to. But that is the basis of a perfectly functional Nile Red based microplastic picking tool, which can allow you to look at your samples, maybe soil samples, mud samples, sand, whatever it might be, stain it with a little bit of Nile Red, illuminate it with blue light, and then by looking with an orange filter, you can observe your sample, see what's fluorescing, and that allows you to pick out the objects that are likely to be microplastics from the sample, and it just highlights them really well so you can see what you're doing. If you want to go a bit more sophisticated, maybe you have access to a fluorescence microscope. Most fluorescence microscopes are designed to work with transmitted light, so they're really good for very small microplastics, but maybe not so good for larger microplastics that typically will be quite opaque and they don't let the light through very effectively. If your microscope uses reflected light, it will likely work much better for microplastic detection. So this particular one is showing optics with a dichroic mirror that sends the light down onto the sample, and then the emitted fluorescence comes back up through an emission filter to your eye or a camera as the detector. And fluorescence microscopes are very widely used, particularly in biology. So many biology departments, if not chemistry departments, will have fluorescence microscopes. But I just want to come back to this issue about solvatochromic shifts and what color your Nile Red fluorescence is actually going to be. Because if you use one of these much more sophisticated fluorescence microscopes, it's quite easy to miss a lot of the output fluorescence from your samples, because some of the very, very commonest fluorescence kind of uses in biology rely on detecting green fluorescence. So fluorescein, for instance, is very widely used as a labeling reagent, and its emission is in the green part of the spectrum. So typically, in a fluorescence microscope setup, you have an emission filter here, which is a relatively narrow band green filter. So it's only going to let through green light in a relatively narrow range of wavelengths, which is shown here in this red box as an example. And the problem is, if your Nile Red is adsorbed onto natural environmental microplastics that are probably surface oxidized, they're not quite as hydrophobic anymore as they once were, they're likely to have their brightest fluorescence in the orange and red part of the spectrum. So if you're looking in the green window, you will miss almost all of this light. And so you might think that there aren't any fluorescent objects, or that they're very, very weakly fluorescing, so much so that you think they're not plastics. But actually, you simply made the error of looking just at the very, very, very bottom end of the tail of the fluorescent emission peak. So it's very, very easy to miss the particles. So you always bear that in mind. If possible, use a variety of different emission filter sets so you can look at different wavelengths in different parts of the range. And that will give you a much better chance of making sure you haven't missed anything. Okay, the thing that possibly I've done the most of is building your own DIY imaging rigs. And I've got two photos here. On the left, this is the original imaging rig that I built in the lab. And some more details of this particular rig are available in the 2017 Scientific Reports paper. It's in the supporting information. And this is actually built using the head of a simple binocular microscope, just like one that I showed you in the slide earlier. It's got a third port, so we've got a camera attached to it so we can take photos. We've got a blue light source. It's one of those crime lights again. At this point, it was just held in a retort stand and pointed at the sample. And then the final part of this rig is an inexpensive micro milling engraving machine. So these are sold by a whole range of different companies. They're all manufactured in China. And it gives you very, very cheap access to automated XYZ motion. So this doesn't have the precision or sophistication of a piezoelectric motion stage that you might have in a high-class confocal microscope or something like that. But it does very decent motion control in a very reproducible way, which you can automate with a simple computer program. So you can use this to move your imaging device, the microscope head and the camera. You can move it around over the top of your sample. It's a filter in this case. And that allows you to image the filter as a number of photos, as a montage, if you like, to connect together. So that gives you access to lots of simple imaging that you can use for research work. On the right here, we've got a more sophisticated rig. So this is my current design version. So we now have a high quality Canon macro lens. I've clamped the light source so that it tracks with the camera. So you always get really uniform lighting. And we've got better, more sophisticated filter holders. But this is all basically home built, put together from very simple parts that you can make yourself or buy. What does it cost? Well, to build one of these rigs, if you buy all the parts new and put them together, costs about £2,800 plus an old computer. And the main cost of this is the imaging lens, the macro lens, and the crime light. If you use an adaptive microscope, as I did in my prototype version, you can save most of the money of that if you have one available. And with a bit of careful work, you can probably use much cheaper light sources than these crime lights. So there's great opportunity there to make this at much lower cost if you need to. Once you've got your images, you can either observe them manually and count them. And we've done an awful lot of that, and I would recommend it because it's very reliable. But you can also use automated image analysis tools. And we've done quite a bit of work with this. There are a number of papers in the literature from other groups that have worked on this. But the bottom line, I would suggest to you, is that you really need to take care with this because it's fraught with complexities about detecting what a bright object is relative to the background. And depending on how you set up your automated system to do that, you can make the number of particles counted be any number you want it to be. So it's not very objective in that sense, and you really need to be careful how you set that up and validate it if you're going to use automated counting.
Andrews, please, can you round up in 5 minutes so that we can have time for question and answer?
Yeah,
Thank
okay.
you.
I'll just say something about this and then I'm done.
All right,
so I've gone on very slow somehow.
Yeah.
Okay, the main issue, the main criticism of Nile Red staining methods is the fact that you can get false positives and also false negatives that I've mentioned before. And it's absolutely true that Nile Red has very non-specific interactions with plastic surfaces. Lots of other things can stain, including biological materials, which might be present in lots of your samples. So you need to think about that potential problem, and you may need to pre-treat your samples in various ways. So we routinely use density-based separation. We often use digestion methods in order to remove some of these natural materials that might be interfering with the detection. And you always need to consider what you might need to do with your sample in relation to where the sample came from and what's likely to be in the sample that you're looking at. And in order to be confident, you really need to validate whatever methods you're using by spiking them with known microplastics of different types and sizes. And if possible, also use vibrational spectroscopy on some of your samples to ensure that you have an understanding of the relationship between the Nile Red numbers that you're finding and what you find from the vibrational spectroscopy. Okay, I'll just go on to this one. So this is what a typical Nile Red detection workflow would look like for typical environmental samples. You need to collect them, obviously. There's a whole art around that. Once you get them back to the lab, you'll need to dry them, probably do some density separation to extract the likely microplastic particles, a filtration step, probably onto nitrocellulose filters so that you can digest your sample, filter and all, to remove organic material, and then filter again. We generally use polycarbonate filters because we find they work really well for this. And then finally, staining in situ with Nile Red on the filter. And then you can take the filter directly to an imaging rig or a microscope to look at and count the number of fluorescent objects. And this is what the sample might typically look like. So this is it's a very old image. It's not a very good image, but it shows some really nice bright microplastic particles here. And also, if you look more closely, you can see lots of small fibers. And in fact, you can even go down to, certainly sub 20 micron particles if you really zoom in and look carefully at these images. So it's a really good way of highlighting probable, possible microplastic particles that would be really difficult to observe just by eye. If you looked at this by eye, you would undoubtedly miss a lot of these smaller particles. Okay, so to summarize, it's not a perfect method, but it fulfills many useful criteria for rapid, inexpensive screening approaches. And that, I think, is what it's best suited for. So you can do lots of rapid counting methods if you want to do spatial surveys, temporal surveys, and monitor trends, changes, and so forth. So it's really good for that kind of analysis. But what it can't do, of course, is tell you the identity of the microplastics themselves. So if you're interested in that, you really need to combine with other techniques, such as vibrational spectroscopy, to get to that information. Okay, I think I'll stop at this point because I think it's important to leave a little bit of time for questions. So the Malaysian network will have to wait for another day. I can maybe come back and talk about that another time.
Oh, thank you very much, Andrew, for a well-detailed presentation. In fact, my first question is about the Malaysia microplastic network. I was expecting that you'll be able to elaborate more on it before we go into the detail of the Nile microplastic detection. Can you just maybe in 2 minutes just give some brief about what you are doing in Malaysia? Thank you.
Yeah. Okay. Maybe I'll just share a couple of slides very quickly then. Okay. The network currently is based in 2 centers in West Malaysia in Terengganu and in Kuching in Sarawak in East Malaysia. So they're the kind of hubs, if you like. And associated with those, we have a number of other partners, 10 currently, but the number is increasing all the time. And these are other universities and NGOs that have linked up with the network to benefit from its analytical capabilities or its expertise and understanding in various different aspects of analysis. Where do I have? Yeah, so just to clarify, we built lots of analytical toolkits for them. Well, 5, not lots, 5, including imaging rigs, home-built imaging rigs like the one I just talked about, home-built manifolds, separator devices, vacuum pumps, glassware, everything that they needed got packed in 10 of these shipping crates. So each kit is 2 crates worth of gear. And the idea is that they have these kits in the hub centers, and then there are some additional kits floating around the network, which are available to loan out to other organizations, institutions, to be used for analysis. So the other 3 kits are currently all in other university departments around Malaysia being used for microplastic analysis. And perhaps the other important thing to emphasize, we also produce some training video or a training video, and you can find that on the Malaysian Microplastic Network website. I can maybe share this after the talk. If you go to this website, you can get to this page, which will then take you to the YouTube channel, where you can find a training video about using Nile Red detection and some of the things you need to be careful with, and some sort of practical advice on using it. So that's a resource that you might find useful, that we produced for the Malaysian project, but we hope it's useful much more widely. Yeah, hopefully that might have answered your question.
All right, thank you. I want to give chance for others. I'm sure some people have 1 or 2 questions. I think there are about 2 questions already in the chat box. But please, if you have any question, can you just unmute yourself and ask directly so that we can save our time? If you have a question, please unmute yourself and ask your question.
Yeah, sorry, I can't actually see the chat at the moment, so somebody will have to read it out to me.
Is Anna here? Anna, are you on?
Hi, yeah, I'm here.
Yeah.
But I think Andrew
Hi, Anna.
already, hi. I think Andrew already touched upon it. It was quite early in the presentations I asked this
Okay.
question. So it was mostly about, so thinking about what would be the best settings for Nile Red imaging in as a whole, because if we you were talking about when we have just the green fluorescent microscopy, then we're going to have some polymers as well, like you're talking about, whether it's particles, but also even pristine PET and polyamides, they have the redshift.
Yeah,
so
absolutely.
they would be much more duller under the green fluorescence. So I'm just thinking, what in your opinion are the best, like if you have to choose a single setting, what would be the best setting for the imaging?
If you were buying it, I would just buy an edge filter, as you suggested in your chat, just an orange cutoff filter, just like the ones I showed for the black and white photography filters, 530 nanometer orange Hoyer filter, something like that.
Yeah.
And I'm sure most microscope manufacturers will sell you one of those. And that has the advantage that it just cuts off everything below that wavelength. So you get rid of all your blue excitation light, but you can see the yellow, the orange, the red, even the little bit of the, well, kind of orangey, yellowy green, perhaps, part of the spectrum. So that I think is probably the best option. Otherwise, I would just encourage you, if you're using a fluorescent microscope that's got narrow band filters that just measure in a quite restricted range of wavelengths, don't just look in one window. So I would go for something, if I had to pick one, go for something that's kind of orange red colored.
Okay.
Kind of 580, somewhere around there. And that will probably pick up the biggest number with the most brightness and intensity. But yeah, it's always an issue that you need to keep in mind, because this solvatochromic shift is interesting, and originally I thought it would be really useful, but actually in this respect it's quite inconvenient, because it means that you're never quite sure where you should be looking.
Yeah. Thank you.
Thank you. Please, Isaac, please, can you unmute yourself and ask your question? We have about 2 questions to round up. Isaac, can you ask your question now?
Yes, hello, can you hear me?
Yeah, good. Go ahead.
Yes, thank you for the talk. So you indicated that oxidized microplastics don't fluoresce so strongly. So I was just thinking, could this property be applied to kind of tell the age of microplastics in the environment, depending on how strongly you see the fluorescence? Can we sort of grade the intensity of the fluorescence to match to the age of the particles?
I don't think you'll be able to do that for 2 reasons. First of all, I said that oxidized microplastics can cause problems, but they do often still fluoresce strongly. It's just that they're more polar on their surface because of the oxidation. So you tend to get this red shift of the fluorescent spectrum. So it's more about the color than the intensity. And the intensity is very dependent on the surface properties of the particle, how much it's reflecting, how much it's scattering, and so forth. So I don't think, I mean, you could probably design a lab study that would allow you to do something a bit like you're proposing, but I don't think it would work on real samples where you don't know anything about their history and you don't have anything to compare them with.
Thank you,
Okay,
Andrew.
thank you.
Please, can we take the last question? Okay, please, Gezali, I'm sorry if I didn't get the name right. Gezali, please, can you unmute yourself and ask the question? Are you there? Gezali, are you there? Okay, because of our time, we need to round up. Please, if you have any other question, feel free to get in touch with Andrews. I'm sure you'll be able to handle that effectively and more in a comprehensive way. Want to thank everybody for attending this webinar. Next month, we are going to have another talk, and I will definitely be handling that, talking about some aspect, very important aspect of microplastic research that can really help in policy formulation. So I'm sure Oli will communicate with us very soon on that. So want to thank everybody, and please, if you have any presentation that you think can help every member of this group, try and get in touch with the PAN-microplast team. We want to hear your findings. We want to learn from your research. We want to see how we can rub minds together to alleviate the problem of plastic pollution, especially in Africa. So please try and get in touch with us. We want to have you on this platform to also present some of the studies that you are carrying out in your laboratory. So I want to thank everyone once again. Thank you very much, Andrews Mays. We appreciate your time and the effort to put this presentation together. And I'm sure that we have a lot to do together in the nearest future. Thank you everyone for attending this program. See you next month.